What's up? I'm Vin, and today I want to go through an AP Calculus ABBC Unit 5 practice test. I'll leave a link to a copy of this test in the description below, so let's get started. Now for part 1, the multiple choice, we're only going to use the calculator for questions 6 and 10. So first up here, we have a table of values for twice differentiable function f of x. Which of the following must be true? So for this one here, let's look at the first few answer choices. We have f of x has no critical points on the interval 0, 6. So what I like to do for questions like this is draw it out. Think about if there's a way for us to contradict these answer choices. And we have f of 0 is negative 20. And then we have f of 1 is negative 12, which would be, let's say, over here. And let's say I draw this in a random way. I have this go up, down, and then back up like this. Well, choice A is saying that f of x has no critical points on the interval from 0 to 6. And if we look here, the way I drew this, there's a critical point right there, a point where the slope is equal to 0. So we actually have two critical points. So choice A is out because this is assuming here that we're just always increasing. And choice B is essentially saying the same thing here. If f prime is always positive, that means f is increasing specifically on the interval from 0 to 6. But notice the way that we drew this, see how we went up, down, and then back up? This contradicts choice B as well. And then what we have next is the graph of f has no points of inflection. Well, if we look over here, notice at this point right here, where the graph switches from concave down, notice it's frowning, and then the graph starts smiling here. So when we have that change, that is a point of inflection. So choice C is out, and just by that, choice D is our answer by elimination. But let's see, why is choice D definitely true? Choice D is shouting out the mean value theorem at us. So the way the mean value theorem works is if we have a continuous and differentiable function, which this statement here guarantees that we have f of x being both of those, then at some point the instantaneous rate of change is equal to the average rate of change, which in this case is equal to 4. And if we just wanted to verify here, we could find the average rate of change, f of 6 minus f of 0 divided by 6 minus 0. And now just use the table, we're going to have 4 minus f of 0 is negative 20. And we're dividing by 6 minus 0 is 6, and then 24 divided by 6 is 4. So there's that average rate of change we were looking for. Choice D is definitely our answer. So question 2, we have f of x, k is constant, and for what values of k, if any, is f strictly increasing on the interval from negative 1 to 1? And if f is strictly increasing, we're going to have f prime is greater than 0 on this interval. So what we could do is find f prime, and we're going to use the quotient rule. So we have x squared plus 3 on top. And we're multiplying by the derivative of kx, which is k, because k is constant, minus we have kx times the derivative of the bottom is 2x, and we're dividing by the denominator squared. So we have x squared plus 3, and this is being squared. So we could simplify the top a little bit. If we distributed, we'd have kx squared plus 3k, and then we would have minus, if we multiply these out, we're going to have 2k x squared. So this will simplify a little bit nicer. We could combine the first and last term here, and we'll have 3k minus combined like terms. You're going to have kx squared like this over, we have x squared plus 3 squared. And now we could just factor out the top here. We could take out a k, and we're going to have 3 minus x squared on the inside. And on bottom, we have x squared plus 3, and this is being squared. So at this step, if we analyze, the bottom factor squared is always positive because x squared plus 3 is always positive, and we're squaring it. So it's still going to be positive. And now be mindful, we're on this interval from negative 1 to 1. So if we had to find critical points here, we could. The critical points would occur when the factor 3 minus x squared is equal to 0, which would give us x equals plus or minus radical 3. So if we wanted to make a sign chart for f prime, we could do this. But in this case here, it's actually not going to be necessary because the subinterval we got was from negative 1 to positive 1. And notice that's between the critical points here. So we don't have to actually use any test values necessarily. If we just do a sign analysis from negative 1 to positive 1, think about it. Any x value between negative 1 and positive 1, if you plug it into 3 minus x squared, it's going to give you something positive. Because let's say you plugged in x equals 0, you'd have 3 minus 0 is 3. If you plug in the endpoints, negative 1 and positive 1, you'd have 3 minus negative 1 squared is 1. This would work out to 2, and then 3 minus 1 squared would be positive 2. So no matter what we plug in for x between here and here, that factor is always positive. So then now we just have to do the sign analysis. F prime of x is greater than 0 on negative 1, 1 implies that this last piece, you see how we have a positive and a positive, that means this last piece, k, also has to be positive. K has to be greater than 0. So choice B is definitely our solution. Now, k equals 0 is no good because if you plugged in k equals 0, then f prime would just be always equal to 0. So it wouldn't be strictly increasing. And if we plugged in a negative k value, we would have a negative times a positive over a positive would be negative, and f prime would be less than 0, so it would be decreasing. And let's say this didn't make a ton of sense. What you could do is you could plug in a test value, let's say at x equals 0, and simplify things a bit. And if you plugged in 0 to the derivative, f prime of 0, if you were to plug in here to this simplified form, would give you k times, we'd have 3 minus 0 is 3, over, we would have 0 plus 3 and then squared would give us 9. So this would give us 3k over 9, and what we need to happen here between -1 and 1, we want f to be strictly increasing. We would need f prime at 0 to be positive, and this would only be true if we had a positive k value here. So B is definitely our solution. So question 3, we have a portion of the graph of f of x, and f of x is twice differentiable, and we want to know which of the following statements is true here. And we have a statement about f prime, and f double prime. So we have to know the difference between all of them. Well, here, if I just look at f of 1 first, notice f of 1 is the function value, which is the y value at x equals 1, which is 0. And then if we look next, f prime of 1 would be the slope of the line tangent to the graph at x equals 1. And what I notice here is that if we were to draw in a tangent line like this, notice that the slope of this line would be positive. So f prime of 1 would be greater than 0. And then f double prime of 1 talks about the concavity. Okay, so this is talking about the concavity at x equals 1. And what I notice here is that we have something concave down when our graph looks like it's frowning at us, and our graph is concave up when the graph looks like it's smiling at us. And notice here, this looks like a frowning graph. So this would tell us here that f double prime of 1 is less than 0. So now we're just going to order these from least to greatest. Notice that f double prime of 1 is negative, so that's the smallest. And then f of 1 is in the middle because it's equal to 0. And then the positive value, f prime of 1, would be the greatest here. So we're going to look for f double prime of 1 to be first. F of 1 is in the middle. And then f prime of 1 would be the greatest here. So choice A is our solution. Question 4, for what values of x is the function f of x increasing? So what we need to look for is when is f prime greater than 0? So I would start by taking the derivative here. We're going to use the power rule. So the 3 comes down, and that's going to cancel out the 1/3, leaving us with x squared. The 2 comes down to wipe out the denominator 2. We're going to have minus 3x, and then we're going to have minus 4. The derivative of plus 2 is 0. And this I would actually factor. This is going to factor nicely to x minus 4 times x plus 1. And then if we set f prime equal to 0, this tells us that our 2 critical points are going to be at x equals, and we'll have -1 and positive 4. So now we can make a sign chart here for f prime. And we're going to mark it at the critical points, -1 and 4. Now, a nice little shortcut to these, what I think of when I think of our derivative f prime is a quadratic, and it's a positive x squared, which means that it's a smiling parabola. And the roots were -1 and 4. So this is a sketch of f prime that I think of in my head. So this is a sketch of f prime. And the behavior of this graph is, notice that the y values are positive, then they go under, so they're negative, and then they're positive again. So that's how I know my sign chart is going to look like this. And that tells me the behavior of f is that f is increasing because the derivative is positive, and then f is decreasing between -1 and 4 because the derivative is negative, and then from 4 to infinity, f is increasing again. So this is just a little trick I use to create the sign chart. Otherwise, what you have to do is you have to plug in test values. Like let's say you plugged in 0 to the derivative. You would have f prime of 0 is equal to 0 minus 4, which is -4, and then you would put your minus here. But once again, if you could imagine the graph in your head, I think that's just a much faster way to fill out the sign chart. But now, if we're looking for where f is increasing, we're looking for where f prime is greater than 0 or where f prime is positive, which is going to be on these intervals here. We have we have x is less than -1, or we have x is greater than +4. And now we just scan the answer choices here, and this is going to work out to choice B. So question 5, we have a graph of f prime, the derivative of f, and what we have is the line tangent to the graph of f prime at x equals 0 is vertical, and then we have f prime is not differentiable at x equals 1. Which of the following statements is true? Well, let's just draw that in over here. So at x equals 0, we have a vertical tangent, and then we have that f prime is not differentiable at x equals 1, so we have a sharp turn here. Now, one thing, when we look at choice A, f prime does not exist at x equals 0. So they're setting a very dangerous bear trap for us. We have to be careful. Even though we have a vertical tangent here, that would tell us that f double prime of x does not exist at x equals 0. So then choice A would be true, but this is just a graph of f prime. So if I want to know what is f prime of 0, That's the y value at x equals 0, which is 0. So choice A is no good. Choice B, we have f has a point of inflection at x equals 1. So for this one here, you have to be very careful with how you interpret stuff. Just know point of inflection, what you should be thinking of is that f double prime changes signs. So we need a sign change in f double prime. This is a big idea. So what you want to think about is how many different ways could you say f double prime? Well, the main way is just to say f double prime. But then after this, we could also say that when we take the derivative of f prime, that gives us f double prime. But in calculus, what is the meaning of the derivative? It tells you the slope of the function at a specific point. So if we found the slope of f prime, that would also tell us f double prime. So what we're really looking for here is when does the slope of f prime change signs? Okay, so that's what we're looking for on the graph here. This is the best interpretation we could use. And when you want to look for a slope change, you're looking for when the graph switches from increasing to decreasing or from decreasing to increasing at a specific point. So notice here at this location, the graph is going up, so it has a positive slope, and then immediately the graph starts to decrease. So see how the graph changes from increasing to decreasing at x equals 1. So that would tell us that we do have a point of inflection because the graph of f prime changes from increasing to decreasing at x equals 1. So now let's see why the other answer choices are no good. So here it says f prime has a local maximum at x equals 0. But think about what that means. For choice C, local maximum, you're looking for when f prime goes from positive to negative. But watch what happens here. At this location, the graph is going from negative to positive. So we'd actually have a local minimum here. So this one is out. And then we have f of x has a local maximum at x equals 1. We have to be very careful. This is yet another bear trap. And for this one, students look and say, oh, local maximum, I'm looking for a hill or a high point. And they say, oh, there's a high point, but be careful. If it said f prime has a local maximum at x equals 1, then it would be true, but it says f of x. So this one is out. We need, once again, a sign change in f prime from positive to negative. So we could actually say here that at x equals 2, we have a local maximum because f prime is changing from positive to negative at x equals 2. So choice B is our solution. So question 6, we want the local minimum of g of x on the interval from 0 to 4, and we actually have g prime here. So we're going to go to y equals, and we're going to type in g prime. We have cosine of 1/3 x squared. And let's say we look here at the graph from negative 10 to 10. This gives us way too much info. We just want to know what's happening from 0 to 4. So if I go to the window, I'm going to switch the x minimum to 0, and I'm going to switch the x maximum to 4. And then what we could do is we could also shrink the y values here. Let's say we just want to go from negative 3 to 3, because all we're looking for is a sign change here. So this will make the picture as big as possible. And if we look here, we have 2 points of intersection, but we have to be careful. The first one would actually tell us a local maximum because the graph is changing from positive to negative. And I promise you, if you were to find this one here, let's say you press enter before, you go after, press enter a second time and a third time, see how you get 2.171. So A is a very dangerous bear trap. The one that we need is the second point of intersection because that's where the graph changes from negative to positive, the graph of G prime. So we're going to go over here before, enter, after, enter, and enter a third time, and we're going to have, when we round, 3.760. So choice C is our answer. So for question 7, you have to know a little bit about curve sketching. So when you have f prime is negative and f double prime is negative, I like to think of these as the 4 emojis. But what we have is when we have a positive first derivative and a positive second derivative, our function is going to be increasing and concave up. So this is what the first shape would look like. If you had a positive first derivative and a negative second derivative, you'd be increasing but concave down. So this would be our, I like to call them emojis. I don't know, they just remind me of emojis. And then the next two cases here, you could have a negative first derivative and a positive second derivative. So you'd be decreasing but concave up. So here is our third emoji. And then the final one, which matches this, a negative first derivative and a negative second derivative, our function would be decreasing but concave down. So it would be frowning at us like this. So when I'm going for questions like this, I just think of the 4 emojis here. And if we have a minus minus, we're looking for a graph that looks like this. And you could see that choice A fits the description here. Not only is our function decreasing, but the slopes here are decreasing as well. They're becoming more negative as time goes on. So choice A is definitely our answer. So question 8, we want to solve for the x value where g of x has a point of inflection. So we're looking for here, when does g double prime change signs? Okay, so this is something that you have to show up to the AP test knowing your vocab, and point of inflection tells you to find the second derivative. So we have g prime of x, and here we're going to use the product rule. We have the product rule is u prime v plus uv prime. So let's do that here. So we have the derivative of 3x is 3 times e to the x, plus we have 3x times the derivative of e to the x is e to the x. And for this, before I find the second derivative, I would actually factor this. But I would just take out e to the x like this. I'm going to leave the 3 on the inside. You'll see why a little bit later. So you have 3 plus 3x like this. And now when we take the second derivative, it's in a form here that's much easier to work with. We could just do the product rule once more. So now when we take the derivative, we're going to have, let's say here, the derivative of the first term is e to the x. And then we have 3 plus 3x like this. And then plus we have e to the x times the derivative of the inside is just 3. So from this step here, now we could factor out e to the x. And we're going to have e to the x times, we have 3 plus 3x, and then plus 3 like this. So this is our second derivative, which we could clean up a bit. G double prime is equal to, we have e to the x times 3 plus 3 is 6, and then we have plus 3x like this. And now we could set our second derivative equal to 0. And one thing to point out is that e to the x is always positive. Okay, so we're not going to get any roots out of e to the x. Just think about the graph of e to the x. It's just always going up like this. So e to the x is always positive. However, the second factor, the 6 plus 3x, can be set equal to 0. And this would give you 6 equals negative 3x, which would tell you x is equal to negative 2. Now, right away, I could see that this is going to be choice B because there is no answer choice that says there is no such value of x. But if we had to be a little bit more thorough with this, what we could do is make a sign chart at x equals negative 2. We could mark it. And if we were to plug in a test value here, let's say less than negative 2, something like negative 3, and you plug it into this here, well, this is always positive. And if you were to plug in negative 3, you'd have 6 minus 9 is negative 3. And then if you plugged in something like 0, you have e to the 0 times 6 plus 0, which would be positive. So there's our sign change in G double prime. So we definitely have a point of inflection at x equals negative 2. So question 9, we have a graph of y equals f of x here. So let's just label this. This is f of x. And we want to know which of the following could be a graph of its derivative. Well, there's a few strategies we could go with, but one thing I noticed here is that f of x is increasing, which would tell us that f prime has to start off positive. And then f is decreasing, which means f prime would have to go negative. And then f is increasing once more, so f prime would have to go back to being positive. And just using that feature of f prime, we need a graph that starts positive, goes negative, and goes positive again. Choice D is the only one that does that. Choice C, it starts negative, then goes positive, and then negative. So this one is out. This one goes positive, negative, positive, negative. So that's too many sign changes. So A is out. And this one really is going nuts. It's negative, positive, negative, still negative, and then positive, negative. So that's too many changes. This one is out. So choice D is definitely our answer. If we wanted to use more features here, notice also that the graph starts off concave down. That the graph is concave down. This looks like our point of inflection where the graph switches to concave up. So if F is concave down, this tells us that F prime has to be decreasing, okay? Because f prime is the slope of the graph, would have to be decreasing here if we're concave down. And notice that once again, we have f prime, here's our graph of f prime, starts off decreasing until it gets to 0, our point of inflection. And then at 0, the graph starts to increase. So choice D is definitely our solution. So question 10, we have a rectangle that's inscribed in a parabola. Here's the equation for the parabola. We want to know what is the maximum area of this rectangle. So optimization questions can be a bit tricky, but you want to think about what formula are you trying to find the maximum or minimum of. So the first thing that jumps out at me is area of a rectangle is length times width. But then the goal is to turn this into a function of x. So we want to write our area function as a function of x, or it could be a function of y. But let's go the x direction. So here what we have is we have a rectangle, and the area of a rectangle is once again length times width. So we have to describe the dimensions here. Well, notice that on the parabola, any point we could call xy. And the way that we get there is we go to the right x units. So we're going over x from the origin, and then we're going up y like this. So this gives us part of the rectangle, but what we have to be careful about is that this is symmetric. So this distance would also be x. So then the area would be equal to the length times the width. And the length we could say is x plus x, which is 2x, times the y value going up to the point xy like this. So our equation would be 2xy. But notice this is not a function of x because it has an x and a y. So we need to make a substitution. So the area as a function of x, which we have written underneath, so let's just write it over there. So the area as a function of x would be 2x times y is determined by the parabola, and we have 9 minus x squared. So we just make the substitution. Now, one thing to be mindful of is that this parabola, we could find the roots very quickly. The roots would be -3 and 3. So let's say we focus on the positive section here. When we want to find the x value that makes this rectangle maximum, let's focus on the domain here. We'll say our domain is going to be from 0 to 3. So from 0 to 3 would be an appropriate domain. So we're trying to find the maximum value of a of x on this space here. So now let's use the calculator to find the max. We're going to press 2x, and in parentheses, we've got 9 minus x squared like this. And now when we press graph, we have too much going on. So I'm going to go to the window and switch the x minimum to 0 and the x maximum to 3. And the y value is cut off. So let's say I just type in something like 40, something that's over all the answer choices. And now I press graph, and we can very clearly see the maximum here. So I could just press second trace 4 for the maximum, since this is a graph of a of x, and we want to find what is the max value of a of x, which represents the area of the rectangles. And notice here that the max is going to be 20.785, which right away gives us choice C. But let's say we wanted to include derivatives in our solution. Well, then we could just go over to the y2 and press math 8 to take the derivative of the first equation. And the shortcut here would be to press alpha trace and then y1. So we're going to take the derivative of y1 with respect to x like this. And then I'm going to turn off the first graph by pressing enter on the equal sign. And then when we graph a prime, notice that we have one point of intersection here, and there's a sign change in a prime from positive to negative, and there's only one sign change. So that means that we have our local maximum is also our absolute maximum. And once again, this is a valid explanation because it's the only critical point on the space from 0 to 3. So not only is it a local max, it's the absolute max. So I press enter before, after, and then a third time, and notice this would be our x value here, our critical point. And then if I wanted to plug it back into the function, this critical value here, I could just press alpha trace, and then y1 was a of x, and I could plug in, I'm just going to put a parenthesis, I could plug in this critical point, close it and press enter, and we get 20.785. So choice C is definitely our solution. So let's move on to the part 2s, and calculator use is not permitted. So for question 1, we have a graph of f prime, and we're given a domain of all real numbers where x is between -2 and 4. And here's the graph of f prime, and we want to know for what values of x does f have a relative minimum, and then later on we want to see when does f have a relative maximum. So my thought process for the first 2 questions here, or parts A and B, is for relative minimum. If we want a relative minimum, what we're looking for is when does f prime change from negative to positive. And since we have a graph of f prime, if we want to see when the graph goes from negative to positive, we should look at the x-intercept here at -1, and notice that there's a sign change from negative to positive at x equals -1. So relative minimum, I'm thinking we have one at x equals -1, and then we just have to write our argument. But then for part B, we want to know for what value of x does f have a relative maximum. And for relative maximum, what I'm looking for is when does f prime go from positive to negative. So this is the first derivative test. And if we see here at x equals +1, notice there's a sign change from positive to negative. So this is our solution to part B. Now, one thing to point out here, when the questions tell you to explain your reasoning, you just have to make sure that you write an actual sentence here. But remember, to argue why we have a relative minimum and maximum, we have to make mention here of our first derivative changing signs. So now for part C, we want to find the intervals where f is concave downward, and we're going to use f prime to justify our answer. And for this here, what I'm thinking about, when I hear concave down, what I'm thinking of right away is that f double prime is less than 0. And since we have a graph of f prime, so this is a graph, I'll just label it over here, this is f prime of x, then what we're looking for is we're looking at the derivative of f prime. When is the derivative of f prime less than 0? And think about what is the meaning of derivative. In calculus, the meaning of the derivative is the instantaneous rate of change, or the slope of the tangent line. So here what we're looking at is when is the slope of f prime less than 0. And when your slope is negative, that means your function is decreasing. So we're looking for the intervals where the function is decreasing, which if we look here, starting at 0, the function is decreasing from 0 all the way down here to 2. So that's the first interval. And then if we look here from 3 to 4, the function is decreasing again. So here are the 2 intervals. Now, just know the key phrase in our argument here is that when we say that f prime is decreasing, we're establishing here that the second derivative is less than 0, making f of x concave down on these particular intervals. Now, for part D, we're going to assume that f of 1 is equal to 0, and we're going to draw a sketch of f that shows the general shape of the graph on the open interval 0, 3. So for something like this, what I would want to do is I want to make a supersine chart. And what I mean by supersine chart is I want to record the sine of f prime, and I want to record the sine of f double prime simultaneously. So I'll color code here. I'll put f prime in pink, and we'll put f double prime in blue. And if we look here, let's take a look. We're starting at 0, and we're stopping at 3. And then the significant values between 0 and 3 are going to occur here at x equals 1, because that's when f prime is 0. So we would have at x equals 1, this is a significant value. And then at x equals 2, notice the derivative changes from decreasing to increasing. So we have a 0 slope of f prime, and the derivative changes from decreasing to increasing at x equals 2. So this is another significant value. But now I'm just going to go ahead and record the sign here. And our first derivative is positive between 0 and 1. But then from 1 to 2, the first derivative is negative. And from 2 to 3, the first derivative is still negative like this. So then the next thing I want to do here is record the sign for the second derivative. And if we look at the second derivative, notice that our function f prime is decreasing from 0 to 2, which means that our second derivative is going to be negative there. That's from 0 to 2. So I'm going to put two minuses like this. But then from x equals 2 to x equals 3, the function f prime is increasing. So that makes the second derivative positive, because the slopes here are going to be increasing in value. So now when we have all of this, we want to remember those shapes from before. I said that the general shapes here, I call them the 4 emojis, but we have our function is going to be increasing and concave down. So that means the function is going to be going up, but the curve is going to be concave down for the first portion. And then the curve is going to be decreasing and concave down, which means it's going to take on this general shape. And then for the last interval here, our function is going to be decreasing but concave up. So it's going to look something like this. So now we're just going to go ahead and make a sketch here. So I'm just going to go ahead and draw this out. We have an xy axis like this. So here's x and y, and I'll label this part here f of x, because we're sketching f of x, and we're sketching it from 0 to 3. So I'm just going to go ahead and throw these values in here. At x equals 1, this was a significant value, and at x equals 2. And remember what we had here, we were told to suppose that f of 1 is equal to 0. So this is going to be the point that we're aiming for. And then the first part of the graph is going to look like this between 0 and 1. So I'm just going to go ahead and draw something that looks like this. So here's the first part of the graph here. And then from 1 to 2, it's going to change shape to this. So it's going to be decreasing and concave down. And then for the last part here, it's going to be decreasing concave up. So we're going to have a point of inflection here. And we're going to stop drawing it here once we get to the neighborhood here of x equals 3. And since we're only drawing this on the open interval, I could go ahead and put open circles here like this, because we don't need to consider the rest of the graph. We're only going to be graphing the portion strictly between 0 and 3. So here's our solution to part D. Question 2, we have f of x equals e to the x sine x, and here's our domain. And the first thing we want to do is find the absolute maximum and minimum on the closed interval 0 to 2 pi, and we need to justify our answer. So for this one, we're going to use the extreme value theorem. So let's start here by taking the derivative. We have f prime of x equals, and we're going to use the product rule. We have e to the x times sine x. So we're doing the derivative of e to the x times sine x, and then we're going to add, we have e to the x times the derivative of sine x is cosine x. So we have to start off here using the product rule, and then we're going to factor. So we have f prime is equal to e to the x times we have sine x plus cosine x. So we want to think here, when is f prime of x equal to 0? F prime of x is going to be equal to 0 when the second factor is equal to 0, because e to the x, just be mindful, is always positive. So this piece here is always positive. So if we set sine x plus cosine x equal to 0, this is a no calculator question. We have to know a little bit of trig here. So we could start by subtracting cosine on both sides. So we'll have we'll have sine x equals minus cosine x. And then we could divide both sides by cosine x like this. And on the left side, we could express this as tangent x. And the right side, after cosine over cosine cancels, we're left with just minus 1. So now we just have to remember here, remember ASTC. This stands for all students take crack. No, you could say all students take calculus, but what it really means is that all the trig functions are positive in quadrant 1, just sine and its reciprocal in quadrant 2, tangent and its reciprocal in quadrant 3, and cosine and its reciprocal in quadrant 4. So if tangent is negative, that means we're not in quadrants 1 and 3. We're going to be in quadrants 2 and 4. So then we have to think here, reference angle wise, the reference angle for this, and I'll just indicate that with the subscript r, theta sub r, our reference angle is going to be 45 degrees or pi over 4 radians. But remember, we're in quadrants 2 and 4, so that tells us that our x values, and be mindful we're between 0 and 2 pi, are going to be pi over 4 going into quadrant 2, which would be 3 pi over 4. And then if we're going into quadrant 4, that means we're going to be going to 7 pi over 4 like this. Okay, so this is where we're going to be stopping. And now what we have to do with these values, these are the critical values between 0 and 2 pi. I'm going to go ahead and just make a chart here. So we have x, and we have our y column, or I'll call it our f of x column. So remember, for the extreme value theorem, you have to plug in the endpoints 0 and 2 pi, but you also have to plug in the critical points here. So we have 3 pi over 4, and we have 7 pi over 4. But we're plugging this back into the original function. So up first, we would have e to the 0 times sine 0. Sine of 0 is 0, so this just wipes out. And then next, if we plug in 3 pi over 4, we're going to have e to the 3 pi over 4. And then we have sine of 3 pi over 4. But be mindful here, sine of 3 pi over 4, well, remember, 3 pi over 4 was a quadrant 2 angle, and that's where sine is positive. And sine at pi over 4, the reference angle, is square root 2 over 2. So this would be square root 2 over 2 times, we would have e to the 3 pi over 4 like this. Now, one thing that jumps out at me right away is that pi is roughly 3.14. So I have 3 times almost 3 is 9 divided by 4. So this would be e to the 2.25 power times this number here. So this number here is like a fairly big number, but let me just see what happens when we multiply out the rest of the stuff here. So let's plug in 7 pi over 4 now. We're going to have e to the 7 pi over 4 times, we have sine of 7 pi over 4, and here it is. Okay, so for this one, 7 pi over 4 puts us in quadrant 4, and if we plug that into sine, remember, just cosine is positive in quadrant 4, so I know this is going to come out negative, and the reference angle is still pi over 4, so we'd have negative square root 2 over 2 times e to the 7 pi over 4 like this. So this is going to be a negative number, and e to the 7 pi over 4 is like a very powerful exponent here, because we have 21-ish over 4 without a calculator is about e to the 5th power, and e is like almost 3, and 3 to the 5th power, like this is going to be a pretty big number here. So this is just what's jumping out at me right away. But now when we plug in this other endpoint here, we're going to have e to the 2 pi times sine of 2 pi, and this is going to work out to 0 because sine of 2 pi is 0. So when we're looking for the absolute maximum here, well, just by default here, these are both 0, and this is the only positive, so this would be the absolute max. And then our other term here, the only negative, would be the absolute minimum. So now we could write out our solution. Now remember, the question said to justify our answer, but us finding the critical points here, plugging them into the original function and the endpoints, this is us using the extreme value theorem to justify our answer. So this would get full credit. So for part B, we want to find the intervals on which f of x is increasing. And we did some of this work in part A. We already found the critical points. So what we're going to do is we're going to make a sign chart for f prime. And the critical points that we found we're going to use. So we have 3 pi over 4 was our first critical point on this interval. And then we had 7 pi over 4 next. So if we write the degree equivalence underneath, 3 pi over 4 is 135 degrees. And 7 pi over 4 is 315 degrees. Now, I'm just writing this just in case this is a little bit fuzzy, but what we want to do here is we're going to plug in test values into our derivative, and we're going to plug it into this factored form here. So what I would plug in is something between 0 and 135, like 90 degrees or pi over 2 radians would be really nice to plug in. And the reason I want to plug that in is we would have e to the pi over 2, and then when we plug into sine here, sine of pi over 2 is 1, plus cosine pi over 2 is 0. And then this, remember, e is always positive, e to any power. So I have a positive times 1. So this is going to work out to something greater than 0. So this first interval I'm going to label as positive here. And then a nice value to plug in between 135 and 315 degrees would be 270 degrees. And that's 3 pi over 2 radians. So I'd plug in 3 pi over 2 next. And if we plug that in, we're going to have e to the 3 pi over 2. And then we're going to have in parentheses here, sine of 3 pi over 2 is negative 1 plus cosine 3 pi over 2 is 0, and I would have a positive times negative 1, which would be less than 0. So this second interval here I'm going to label as negative. And now this one might be a little bit tricky. Which angle could we plug in between 315 degrees and 360 degrees? And that would be 330 degrees, because that's a 30-degree reference angle. But in radians, that would be the equivalent of saying f prime at, we would have 11 pi over 6 like this. Because if we go one more pi over 6, that would be 12 pi over 6, which would bring us to 2 pi. And if we plug this in, we're going to have e to the 11 pi over 6, and we're multiplying by, we have sine of 11 pi over 6, and be mindful here that we're in quadrant 4. If we look here at 11 pi over 6 is this angle over here in quadrant 4, and that's a reference angle of pi over 6 or 30 degrees. So I'm really doing here sine of 30 degrees is a half, but we're in quadrant 4, so this would be negative half, plus we're plugging into cosine now, and cosine is positive, and cosine at 30 degrees or pi over 6 radians would be square root of 3 over 2. So now if you think about this here, this is kind of like a tug of war, but radical 3 over 2 is greater than negative half. So I have a positive times, this will be positive, and my last interval here I could label as positive. So now we just have to write out our solution here, and be mindful here, if we want to know where f is increasing, we're looking for where the derivative f prime is positive. So these are the two intervals where f would be increasing. Now this is a small detail, but you may notice that I did include the endpoints here, and this would be because if we plug 0 and 2 pi into the derivative, be mindful that we would get something positive for both of those. So we can include the endpoints in this case, but just know if you were to put open intervals for both sides here, they would actually give you full credit for this. They don't get too picky here on open or close, but this is just an extra detail that for this particular question, we can say our function is increasing at 0 and 2 pi. So for the last part here, we're finding the x-coordinate of each point of inflection of f of x on the interval from 0 to 2 pi. And I'm just going to borrow our first derivative from before, because for points of inflection, we want to find the second derivative. So for that, we're going to do the product rule here. So I'm going to call this our u term, and this is our v term. So we're doing u prime times v. So we have e to the x times sine x plus cosine x. But now to complete the product rule, we're going to have plus u, which is e to the x, times v prime, which is going to be cosine x minus sine x. And now just algebra, we have to factor this out. So we have f double prime of x equals e to the x times, we have sine x plus cosine x, and then the second binomial, we have plus cosine x minus sine x. So this looks very messy, but it's nice here. Sine x minus sine x cancels. And these are like terms. Cosine plus cosine is 2 cosine. So this we could simplify as, we have f double prime of x equals, we'll just put the 2 in front. We have 2 e to the x cosine x like this. And now we want to set the second derivative equal to 0. F double prime, so let's just make this neat. F double prime is equal to 0 when cosine x is equal to 0. So be careful here. Remember, e to the x is always positive. So we're just going to be setting cosine x equal to 0. And this is going to be true when x equals, and the two solutions from 0 to 2 pi, cosine is equal to 0 at pi over 2 radians and at 3 pi over 2 radians. So this is just all unit circle stuff. And now we have to make a sign chart. So let's go ahead and do that over here. So we're making a sign chart for f double prime, and our interval is going from 0 to 2 pi, and we just write our two roots here at pi over 2 and at 3 pi over 2. So what we want to think about here is, remember, our second derivative, this is positive. Our second thing here is always positive. So cosine is going to be the determining factor of the sign of our second derivative. And just remember this once again, we have ASTC. So for this, from 0 to pi over 2, that's in quadrant 1. That tells us all the trig functions are positive in quadrant 1. So cosine would be positive between 0 and pi over 2. So we have a positive times a positive times a positive. So f double prime would be positive from 0 to pi over 2. But then if we go from pi over 2, so let's just be mindful here. This is 0, pi over 2, pi, 3 pi over 2, and then this sends us back to 2 pi over here. But from pi over 2 to 3 pi over 2, cosine is negative because only sine and tangent and their reciprocals are positive in these quadrants. So that tells us if cosine is negative from pi over 2 to 3 pi over 2, we would have a positive times a negative, which make our second derivative negative. And then the last space to check is between 3 pi over 2 and 2 pi, and that's quadrant 4. And cosine is positive there, so we'd have a positive times a positive times a positive is positive. So if we're looking for our point of inflection, notice we have a point of inflection at x equals pi over 2 and at 3 pi over 2 because our second derivative changes signs at those values of x.